Hello students and welcome to lesson 3.06 dealing with covalent bonding and Lewis structures. Up to this point you have studied lessons 3.1 through 3.5, which is focusing mainly on ionic bonding. Now we're going to shift gears a little bit and look at covalent bonding. First, before we do that, I just want to mention the standards that we will be addressing in this lesson. For this lesson in particular, the two objectives that we have is to determine how atoms will covalently bond together based on their location on the periodic table. And then we're going to do some Lewis structures to model covalent bonding. Before you do 306, please go back and refresh yourself on 3.04, which was focusing on valence electrons, because again, those are the ones that are involved in bonding. So if you're not feeling comfortable with that one, definitely review it, watch the video, get some help in the tutoring room if you need, but make sure you're comfortable with the first part of Module 3 before you continue into the second part. Alright, so again, the first thing we're going to be looking at is covalent bonding. Alright, remember we just mentioned a moment ago that bonding is only with the valence electrons. In other words, the outer shell electrons. The inner shells are already filled, so they're not going to be involved in bonding because they don't need any more electrons to be filled. The whole purpose for atoms to bond in the first place is that they want to have filled energy levels, every single one of them. And since the outer energy levels are the ones that are typically not filled, that's where the bonding actually takes place. Now, just a quick review or refresher here. When we did ionic bonding, the first half of Module 3, remember an ionic bond is when you have two atoms, one has a strong attraction for electrons, and the other one has a weak attraction for electrons. And the illustration that we use is kind of like a tug of war. With an ionic bonding situation, you have one person that's extremely strong, the other person is really weak. So when we have a tug of war between those, of course we all know the stronger person is going to, win and pull the rope onto their side. Well, that's the way ionic bonds work. In an ionic bond, the atom with the stronger attraction will take the electron from the one with the weaker attraction for it. So now what you end up with is you have a negatively charged particle, you have a positively charged particle, and of course opposites attract, so you have an electrostatic attraction between the oppositely charged ions, and that attraction between them is what we call an ionic bond. In covalent bonds, instead of it being a full-on win, if you will, in the tug of war, it's basically a standoff. So instead of one atom taking the electron from the other one, they end up sharing them. Alright, so this typically happens between two nonmetals where they both have a strong attraction for the electron. So again, using our tug of war illustration, we've got two people with basically equal strengths or close to equal strengths, and when they do that tug of war, nobody's really wins. So what they end up doing is they basically compromise in a sense, if you want to think of it that way, and they share that electron instead of one taking it and the other one losing it. So there's a mutual attraction for those electrons, and they're going to share them. So of the two, we actually end up with a stronger bond in the ionic situation because the electrostatic attraction is going to be stronger than just having this mutual attraction for the same electron. Alright, so again, just carrying this a little bit further here. Just a little grammar here. The word covalent, co simply means sharing. Valent is for valence electrons. So again, sharing valence electrons, that's why we call them covalent. Alright, sharing valence electrons. The reason, again, that they share those outer shell electrons is so that they have a filled outer energy level. Earlier in the module we learned about this. This is called the octet rule. Atoms want to share electrons to have 8 valence electrons. When they get to 8, That's the magic number, so to speak, to have a full outer energy level. The only exception to that is hydrogen. Hydrogen, because it's on the first energy level, can only have 2 electrons total. So for hydrogen, it's more of a duet rule, where they only need 2 electrons to have a filled or full outer energy level. All right, and a full outer energy level, filled outer energy level, means they are happy, which means they are like the noble gases. And since the noble gases, group 18, already have filled outer energy levels, they're perfectly content and happy the way they are. That's why they don't react. Everybody else is trying to get to that state. So if you look down here at the diagram at the bottom, we've got oxygen, and the blue dots represent the electrons for oxygen in the outer energy level. Okay, we didn't draw the inner energy levels here. We just got the outer energy levels. So you can see we've got 1, 2, 3, 4. Down here we got 5 and 6. So right now, just imagine that the two waters are not there at the moment. The oxygen has 6 valence electrons. And we'll show you here in a moment how we know that, but for right now, just kind of go with me. All right, and again, we just said it wants 8. So oxygen wants to pick up 2 more electrons. Now, if we look at the hydrogens down here, the hydrogen electrons are represented by the green dot. So the hydrogen, right, has 1 electron, and then this hydrogen has 1 electron. Okay, so we have hydrogen with 1 valence electron, 1 electron in its outer energy level. Well, again, we just mentioned hydrogen's the exception to the octet. It's actually a duet. Hydrogen wants 2. So what happens is we get 2 hydrogens that come along, each wanting 1 electron. One hydrogen joins up with this single over here from the oxygen, and then the other one joins with this single for the oxygen. The way I like to think of covalent bonding is you're playing matchmaker, like Cupid. You take the singles and make them into a pair. You make them a couple. Okay? So now when we count hydrogen here, hydrogen has 1, 2 because he's sharing both of these electrons. So now he's got the 2 he wants. Okay, so this hydrogen's got 2, he's happy. Over here, the other hydrogen, he's sharing these 2, so he's happy. And then for the oxygen, he still's got 1, 2, 3, and 4 up here, but down here he's sharing the other 4. 1, 2, 3, 4. So again, that gives him a total of 8, so the oxygen is happy. All right, so they shared their single electrons to make a pair with each other, thereby giving each other a total that they need to be stable. And that's why water has the formula H2O, because we need 2 hydrogens to donate, if you will, 1 electron each to the sharing with the oxygen to get everybody happy. Now, a second ago I mentioned the valence electrons. How do we know how many valence electrons they have? Well, it goes back to the periodic table. All right. So in group 1, which is hydrogen's group, everything in this group is going to have 1 valence electron. All right, in their outer energy level, if you go back to module 2 where we did electron configurations, you remember they all are S1s. 1s1, 2s1, 3s1, which means they have 1 valence electron in that s orbital. Beryllium, magnesium, and calcium, so on down that second group, they have 2. All right, now I'm going to skip the transition metals for a minute. We're going to come over here to the P block. All right, boron. The configuration for boron is 2s2, 2p1. So we've got 2 electrons in the 2s and we've got 1 in the 2p. So total, boron has 3 valence electrons. Okay, and you can see the pattern now, right? Carbon, has 4, nitrogen's group has 5, oxygen's group has 6, fluorine's group has 7, and the noble gases have 8. So again, the noble gases already have their filled energy level, so they're happy just the way they are. Now, before we talk about the covalent ones, let me just go back here and mention the transition metals. Remember, with the transition metals, going back to Module 2, they fill in the previous energy level. So if we go down here to scandium, potassium and calcium fill in the 4s sublevel. When we get to scandium, we now jump back to the 3d sublevel. So all of these electrons are actually going into an inner shell. Since they are going into an inner shell, they are not part of the valence shell, the outer shell. So all of the transition metals for our discussion are going to have 2 valence electrons, because we are only looking at the electrons in the s and p blocks when we talk about valence electrons. And remember, the s block is these first 2 over here. All right, this is the s block, groups 1 and 2, and then over here, groups 13 through 18, that's our p block. Those are our outer shell electrons. Now, as far as the number of covalent bonds, well, if we remember, we're talking about the nonmetals, so we're only talking about the elements over here on the right side of the table, basically groups 14, 15, 16, and 17. Well, if we work backwards here, group 17, they all have 7 valence electrons. And remember, they need 8. So group 17, these guys are going to make 1 covalent bond to get to 8. Oxygen's groups, sulfur, selenium, these elements, they all have 6. To get to 8, they need 2 more. So they're going to make 2 covalent bonds. Okay, you can kind of see the trend here also. With the nitrogen and phosphorus, they have 5, so they need to make 3 bonds. And then the carbon only has 4, so they need to make 4 bonds. Alright, so based on their position on the table, we can predict how many bonds they're going to need to make to get to that octet. And that's going to come in useful when we get to Lewis structures. And we'll talk about those here in a little bit. Now, because some of them need more than 1 covalent bond, we have the potential for what we call multiple bonds. Alright? So we're talking about things like the oxygen, the nitrogen, the carbon, those type of things. Okay? An example would be pure oxygen. Alright? Oxygen is found as a diatomic element. And here's why. If you look down on the bottom, we've got our hydrogen molecule. Again, if we look at the oxygen on the left, he's got 1, 2, 3, 4, 5, 6 valence electrons. Those are the blue ones. And then the one on the right has 6 also. And those are the green ones. 1, 2, 3, 4, 5, 6. Again, like we mentioned earlier, you're basically playing matchmaker. Make the singles into pairs. So we take the single blue and pair it up with a single green, and then we do that with the other one. We take a single green and pair it up with a single blue. Now when we count everything for the one on the left, we've got 1, 2, 3, 4, 5, 6, 7, 8. So he has his 8 electrons now, so he is happy. And the one on the right, again, 1, 2, 3, 4, 5, 6, 7, 8. So he is happy. Everybody's got their 8 electrons. But you see, in this situation, we shared 1, 2 pairs. So because we're sharing 2 pairs, we have a double bond. This leads us to something we need to mention here, diatomic molecule. These are naturally occurring molecules that are always going to be found in pairs. All right, and the reason for that is what we're talking about right now. They want to be stable. Well, if two oxygens get together, they can easily make a double bond with each other and be stable as a molecule, whereas as a single element, they're not as stable. So here's a list of the diatomics. And each of these, again, will be found naturally in the diatomic form because that is their most stable form. So you got H2, two hydrogens getting together, two nitrogens, fluorine, chlorine, bromine, and iodine. All right, so basically you've got hydrogen, oxygen, we should add on that list because we just talked about that one, nitrogen, and then all of group 17. Those will be your diatomic molecules. Now you can also have multiple bonds between different types of atoms. Okay, and here's an example of that, carbon dioxide. The last screen we were just talking about diatomics, but it's not always diatomics that will have multiple bonds. We can also have them between different molecules. Again, carbon, if you remember a couple screens ago, needs four or needs to make 4 bonds to get to 8. So he makes 2 bonds with this oxygen and 2 bonds with the other oxygen. Now, we'll talk more about this here in a moment when we do Lewis structures, but the line represents a shared pair. Okay? So keep in mind that this line is a shared pair. So when you see a line in the structure, that really counts as 2 electrons, not 1. So when we're counting the electrons for the carbon, we've got 2, 4, 6, 8. So he has his 8, and they're all shared in the bonding. And then the oxygens, we've got 1, 2, 3, 4 that are unshared, and then 2, 4 that are bonded, so a total of 8 for that oxygen. And then of course the same thing on the other end. We've got 1, 2, 3, 4 that are unbonded, and then 4 more that are bonded. So he has his 8. Alright, and sometimes instead of unshared, the term we use there are lone pairs. So just some terminology there. L-O-N-E, lone pairs. Alright, and then the other thing with multiple bonds is they have different lengths and different strengths. A nice illustration I like to use for explaining this is rubber bands. Okay? If you take those nice thick rubber bands and you have just one of them and you try stretching it, it's relatively easy to stretch and you can make it really long when you're stretching it. The reason being is it's not that strong. So a single rubber band is relatively weak and you can stretch it really long. So that's just the way a single bond is. Alright, they're relatively weak, so they are long in length, and you can see by our legend here the thickness represents the strength. Okay, so they're weak and they're long. Well, now if we take a second rubber band and put it together with the first one, so now we have 2 working together, we're not going to be able to stretch it as far as we did the first time because they're working together, right? So we're going to have a shorter stretch because they are stronger working together. Again, the same thing works here with the bonds, because in a double bond, now you have the 2 rubber bands. Okay, I'm just going to abbreviate RB here for my illustration. So it's going to be a shorter bond length, and they're going to have a stronger strength. And then of course the same logic would work if we went to 3. If we took 3 of those rubber bands and put them together and then tried to stretch them, we're not going to be able to stretch them very far because they are much more stronger working together as 3. So a triple bond is going to be even shorter and even stronger. Okay, so an important relationship there. Alright, now let's we're going to look at polyatomic ions, but first let's just clarify the difference here. A molecule is a neutral substance of atoms covalently bonded together. And that's what we've been talking about up to this point. Okay, molecules. Remember, molecules only refer to covalent compounds. When we talk about ionic compounds, like you learned earlier in the module, those are called formula units. A polyatomic ion. Well, if we just break the word apart here, poly means many, atomic, of course, atom, and then an ion, like we've already learned, is an electrically charged particle. So basically what that means is we take 2 or more atoms and we covalently bond them together, and they have an overall positive or negative charge. Now you've already seen these examples earlier in lesson 3 or module 3. Sulfate is SO4, right? So there's one sulfur that bonded to 4 oxygens, right? So they are both nonmetals, therefore they're going to be covalently bonded. But to do that, they pick up 2 extra electrons. And now they overall together have a -2 charge. So we have a polyatomic ion. And then that ion, of course, then can bond in an ionic compound with a positive ion. All right, so ammonium, nitrate, carbonate, hydroxide, some other examples, they all are the same situation where we have 2 nonmetals covalently bonded together. But to make the bond happen, they either have to gain or lose some additional electrons, and that's where we end up having the charge. All right, so again, like for the ammonium, it had to lose an electron to make that bond happen, whereas the negative ones have to gain an electron, or 2 or 3, depending on what the charge is, to make that happen. All right, so again, very important to understand that within a polyatomic ion, we have covalent bonds, okay, within the ion, and that's up here in the 3rd bullet. There we go. All right, it's covalently bonded within the polyatomic ion. But then that ion, because it is an ion, can now make ionic compounds with other ions. So if you have a polyatomic ion involved, then you technically have both ionic and covalent bonds. You know, so for an example, if I had NaOH, sodium hydroxide, we typically call this an ionic compound, which is correct. But within that, we have a covalent bond between the OH, and then we have an ionic bond between this whole structure OH and the Na+. Okay? All right, so quick summary. All right, again, ionic bonds exist as formula units, and it's when electrons are transferred from metal to nonmetal, giving you positively and negatively charged ions, and then they have an electrostatic attraction between them. Covalent bonds are going to make molecules, and this happens when nonmetals share their electrons with each other. Again, in both situations, the purpose is to get to 8 valence electrons so that they are happy, stable atoms. And then in a polyatomic ion, we have groups of covalently bonded atoms that act as an ion because they had to pick up, extra electrons or remove some extra electrons to make that formation occur. All right, so now we've talked about the bonding. We need to look at Lewis structures. And we use Lewis structures to basically give us a model or representation of how those atoms are bonding with each other. Okay, so again, it's just a representation of the bonded and non-bonded valence electrons. Again, those are the only ones we're working with. We're not worrying about the inner shell electrons. Mentioned earlier that we use a line to represent 2 electrons that are being shared, the bonded ones. And then all the other electrons we usually represent with dots around the symbols, and those are the unshared or lone pair of electrons. There are some steps that we need to follow, and we're going to actually look at a couple that have been done, and then we'll do one together to draw the Lewis structures. All right, first thing is we take the least electronegative element and we put it in the center. Secondly, we calculate the total valence electrons, write the skeleton structure, complete the valence electrons, compare the totals to make sure we're using the right number of electrons, and if we're not, then we need to redistribute those electrons to make it correct. All right, so earlier I showed you the CO2 Lewis structure. Let's kind of walk through step by step here how we would end up with that. All right, so if we go back to 3.03, in that lesson we would find a chart of electronegativity values. And if we look up carbon and oxygen, carbon, now I'm going off memory, is around 2.4 if I remember correctly, and oxygen is 3.5. So carbon has the lower electronegativity. That tells us it is the central atom in the structure, so that's why we put it in the middle when you look down here at the drawings. All right, secondly, we need to determine the total number of valence electrons. Well, we have one carbon, so that one carbon has 4 valence electrons. We then have 2 oxygens. So remember, one oxygen has 6 valence electrons. Since there are 2 of them, we got to double that. So 4 plus 2 times 6 gives us a grand total of 16 valence electrons that we can use to make our structure. Step 3 then is the skeletal equation. And what that simply means is we just take the other atoms and bond them to the central atom. So we've got oxygen bonded to carbon on both sides. So we've already taken care of 2, 4 of our valence electrons. All right, step 4 is we fill the valences for each atom. So this oxygen, since he's already got 2 involved in the bond, will need 6 more valence electrons placed around it. That is true for the other oxygen on this end. We got 2 there, 2 here, and 2 here. Now the carbon in the middle, since he's got 4 involved in the bond, he only needs 4 more. So we got 2 on top, 2 on the bottom. Now if we count all of the electrons involved, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons total have just been drawn in that structure. We only had 16 to work with, so we've got too many. So we need to get rid of 4 electrons. Okay? So how would we do that? Well, if you look over here on the right, I kind of blew it up here so you can see it better. If we take away the 4 electrons on the carbon, okay, so we get rid of these here. All right, so we got rid of our 4 electrons. Now we got the 16 that we're only supposed to work with. Well, what can we do then to help the carbon out? Well, what happens is each oxygen donates a pair of its electrons to the bond. Okay, so each of those donate a pair. Now the carbon has his 8 electrons because they're all involved in the bonding. So if you look down here at the final structure, we've got the carbon in the middle, double bond on each side. So 2, 4, 6, 8 for the carbon, and then 2, 4, 6, 8 for that oxygen. And then on the other side, 2, 4, 6, 8 for this oxygen. Okay, so just kind of a rule of thumb is if you go over like we just did in this example, then take the electrons away from the central atom and then start making double and triple bonds as needed. And that's how you're going to get the structure you need with the appropriate number of total valence electrons. Because now if we count our valence electrons, we got 2, 4, 6, 8, 10, 12, 14, 16. All of our valence electrons have been accounted for. All right. Here's an example of a polyatomic ion. Okay, so again, if we went to our chart to look up electronegativity values, nitrogen will end up as the central atom. Now, nitrogen is in group 15, so it has 5 valence electrons. Hydrogen's in group 1, so we got 4 of them, so 4 times 1 to get us the hydrogen. Because of the positive 1 charge, to become positive, remember that means he had to give up 1 electron, all right, because the electrons are negatively charged. So we subtract 1 because that was given away. So 4 plus 5 minus 1 gives us 8. All right, so just a quick side note here. If the charge on there is just, for an example, was plus 2, then we would have to remove 2 electrons. So if we're removing 2 electrons, then of course we would subtract 2. So in that case, the math would be 5 plus 4 minus 2. All right, ending up with 7. That's if it was a plus 2. Okay, so just make sure when you're subtracting or adding, if it's a negative ion, that you are using the right number. So for an example, again, just side note here, let's do SO4 minus 2. Sulfur is in group 16, so he has 6 valence electrons. Oxygen is also in group 16, so he has 6, but we have 4 of them in the formula. So we got to multiply that by 4. Since it's a negative 2, that means we gained 2 extra electrons. All right, because again, electrons are negatively charged. So put that all together, you got 4 times 6, 24, plus the 6 is 30, excuse me, and then plus the last 2, so we have a total of 32 valence electrons to work with on that one. That's how you would do the math in step 2 there for a polyatomic ion. All right, so our skeletal structure, we put the nitrogen in the middle, and then bond each of the hydrogens to it. All right, now if we count our electrons, we've got 2 in each bond, right? So there's 2, 4, 6, 8. So for the rest of the steps, it's already done for us. Okay, we have no more electrons to place because hydrogen only needed 2, right? So he's got his 2 here. This nitrogen's got 2. Same thing on the other ones, or the hydrogens, excuse me. The nitrogen needs 8, 2, 4, 6, 8 in the bond. So everybody's happy just the way they are. So that would be our structure for NH4 with a positive charge. Okay, so sometimes that does happen, that everything just is taken care of. You don't have to get into the last few steps, but that would be our Lewis structure there. All right, so this one, let's actually walk through it together. Okay, we got NH3. So again, if we look up the electronegativity values, nitrogen is the lower one, so he will go in the middle. All right, number 2, we need the valence electrons. Nitrogen's group 15, so there are 5. We have 3 hydrogens, each with 1 valence electron. So it's a total of 8. Okay, so again, we're going to put the nitrogen in the middle. And then we're going to draw our skeletal equation. So we're going to bond each hydrogen to that central atom. Okay. Step 4, remember, is to complete the valence, right? Okay, so again, hydrogen only needs 2. So this hydrogen's got his 2 right here in the bond. Same with this hydrogen on the bottom, and same with the one on the right. Now for the nitrogen, we've got 2, 4, 6. So he's going to need 2 dots on top here to get his 8. All right, so we completed the valence. Next step is to check our electrons. All right, check the count. Okay, so we got 2 unbonded and then 2, 4, 6 in bond, so the total count is 8. And if we go back to number 2, or step 2, that's how many we had, is 8. So that is correct the way we have it. So our final structure, we don't have to make any corrections. Everybody is happy just the way they are. And we use the proper number of valence electrons. So that would be our Lewis structure for NH3. Alright, and that's how we do Lewis structures. Okay, so what's next then? Well, make sure you complete the entire lesson for 306, including the introduction, all the example and practice problems. Click on any hyperlinks that you'll see. If you still need some help, please attend one of the open tutoring sessions that we offer. There will also be a review sheet in the Resource Center that you can use. After you feel comfortable with all the material, you do need to complete the 306 lab, which is found in the Activity tab. At the very bottom of the Activity tab, there is a second lab called 306B. You will need to complete that one also. And if you need assistance with either of those, we also offer completion session for each of them. So on your teacher's announcement page, you can check the schedule to see when the next completion sessions are. And again, you can get help to actually finish the assignment itself. Again, those are not tutoring sessions. There are things that you need to do prior to attending, but we will walk through with you the data analysis and answering the conclusion questions, those type of things in those sessions. So again, there are 2 assignments here, 306 and 306B. When you submit them, the 306 lab report is submitted in the 306 assessment slot. And for the 306B, you need to go down to the 4.12 or 4.12 assessment slot, and that's where you will submit the 306B assignment. I hope this was helpful, and we look forward to seeing you again soon.